16.2 Triangle medians. Your teacher will tell you how to draw and label the medians of the triangle in the warm-up. I don't really appreciate being told what to do. But you know what? I guess that's what you guys deal with on a daily basis. So maybe I need to be a little more empathetic. But you know what? I do not. Don't tell me what to do. Okay. So anyways, we did that, and I did do that already. So I don't know why they're telling me a second time to do something I already did. But we did that. So 1, after the medians are drawn and labeled, measure all 6 segments inside the triangle using centimeters. What is the ratio of the 2 parts of each median? So they want us to use some sort of measuring tool to find the distance, the first part to this centroid, and then the distance after. So they didn't use the word centroid. I wish they did, but you know what? Can't always get what you want. It's something you're gonna learn. You're gonna learn in life. So this looks like it is 3.7, and this is looks like it is about 2. Let me double check that. Yeah, let's say like 3.8. That's 2. All right, so I don't see a clear ratio right there. Not an easy one to look at, but you know, human error can always cause some of these things to be a little bit off. Okay, so from here to here, this looks like it's like 3 centimeters, and this one is it's like 1.5. That's clearer to me. All right, that's 2 times 1.5 is 3. Here we got another 1.5, and this is 3. So I guess if this is 2, this is probably closer to 4. I'm also going to hypothesize that this is an isosceles triangle, because if these 2 medians are the same length, that would make sense that it would be isosceles, that the sides they result from, that they connect to, are also the same length. That's just a hypothesis. I don't know if that's true. But it looks to be as though we've got a ratio of 2 to 1. But you know, we just measured that. It was not super accurate. As you can see, it wasn't even consistent for every single one. So I need to, you know, prove this geometrically. So they also added some other labels in. The median from vertex A is going to connect to a point called N. So A to N. So N is 4, 5. A is 2, 1. So I'm going to write that down. A is 2, 1. N is 4, 5. A and N. Because I want to use my formula for a directed line segment. All right, if we remember, I'll write these on the side here. Our x new is going to be x original plus the change in x times that ratio. Our y new is going to equal y original plus the change in y times the ratio. So here we can see our ratio is going to be 2 over 3. Right? If I have $2 and you have $1, if someone said I have $3 to split with you, I'm sorry, that was bad. If I have double whatever you have, right, 2 to 1 is double, and someone says, oh, let's split these $3, I'm going to get 2, you're going to get 1 because I get double whatever you get. So out of the $3 in total, 2 of them are mine. So that's the ratio we want to use. And it's important that we start at A and go to N, because that's the direction, 2 to 1, A to N. All right, so for X, we're going to get our original is 2, Y, our original is 1. My change in X, 2 to 4 is plus 2. Y, 1 to 5 is positive 4. And then I'm going to put my ratio in for both. And you can do these one at a time. I think it's easy sometimes to sort of see how they're set up the same way. But sometimes if you make the same mistake twice, that might not be so helpful. So I'll try and do it a couple different ways when I do these. So we got 2 plus 2 times 2/3 is 4/3. 1 plus 4 times 2/3 is 8/3. Sort of nasty fractions here. I'm going to leave them as fractions because I don't like writing repeating decimals. This will be really the same as saying 6/3 plus 4/3. It's 10/3. Same as saying 3/3 plus 8/3. It's 11/3. So my ratio here will be 10/3, comma 11/3. All right, and then we're just gonna do the same thing a couple times. So just getting some more practice with this. X, let's just do it one at a time this time. X starting, oh, let me get my new coordinates, sorry. BL, so that means the median from B to the another point will be L. So from B, this will be called L. So B is 6,3, L is 2,4. B is 6,3, L is 2,4. All right, it's important we keep that order right, so I'm gonna double check. All right, B is 6,3, L is 2,4, great. All right, my original X is 6. My change in X from 6 to 2, we're going down. So that's a -4. And then my ratio remains 2/3. For Y, my original Y is 3. I'm going to go from 3 to 4, so that's a +1 change in Y, and my ratio remains the same. I'm going to convert this to a fraction already because I can tell we're going to end up with fractions again. So 6 is really 18/3. And then -4 times 2/3 is -8/3. Going to convert this to a fraction as well. That'll be 9/3. 1 times 2/3 is just 2/3. I mean, if you write this as a decimal, it's fine if you prefer that, but I like improper fractions more. Because it's, you know, you can make a lot of mistakes sometimes converting to a decimal. I guess you could make mistakes this way too. But I just like it better. It's a matter of preference. Do whatever you like. All right. 18 minus 8 is 10, so 10/3. 9/3 plus 2/3 would be 11/3. And we can see that we actually end up getting the same point. So that's good. That means that that ratio is accurate. Because if it wasn't accurate, we'd be getting a different value, right? We're assuming that every single median has that directed line segment, that weighted average of 2 to 1. So if we use that same weighted average 2 to 1 in every line segment and we get the same point, then we know that in fact they do actually all intersect at that one point. So there are a lot of different ways to prove something. That's what I love about geometry. All right, C to M. All right, well, C starts at 2, 7, and then I guess this will be M, 4, 2. So 2, 7 to 4, 2. Of course, very important that it's 2, 7 to 4, 2 and not 4, 2 to 2, 7, because then it wouldn't be split the right way. All right, here we're splitting the line sort of like that, where it's 2 to 1. If we go the opposite way, we'd be splitting that line like this, and we don't want to do that. All right, so very important the order that you write these coordinates in. Okay, so our original X is 2. I'm going to do these together just because I find it easier that way. My change in X, 2 to 4, is a +2 change in X. My change in Y, 7 to 2, is down 5. All right, ratio remains 2/3, 2/3. All right, this will be, I'm going to convert both of these to fractions. So that's 6/3. That's 21/3. 2 times 2/3 is +4/3. -5 times 2/3 is -10/3. So I get 10/3 and 11/3 here. So we keep getting the same coordinate, which is good news for us because it means that that centroid really does occur at this coordinate. So 10/3 is really like 3.33 repeating, and that's really like 3.66 repeating. So let's see if that actually is the point. 3.33, it's right about here, and then 3.67 is right about here, and we can see that that is exactly where that centroid is. They did a nice job. All right, I'm going to try this Are You Ready for More? The other ones I've sort of been giving as extra credit because they take so long, but this one is actually pretty quick. So in the image, AB is a median. So if AB is a median, I know that you got a equal size right here, right? And they're both going to be C over 2 in length because it's splitting that side in half. All right, so they want us to find the length of AB of the median itself in terms of A, B, and C. Okay, this is not an easy problem. Not an easy problem at all. So I'm going to do my best to sort of show you how this works. But it's quick. So what I'm going to do is I'm going to construct a median for this triangle here. All right, and I'm allowed to do that. I'm allowed to say that I'm going to draw this line. Let's call this BD. And I'm going to say BD is a median. And I'm allowed to say that. All I'm saying is that it cuts this side in half, and that's fine. So I know that this is congruent to this because it cut it in half. All right, another thing I can see here is that, let me maybe outline this in purple and make it easy to see. If you look at this small triangle here, it's got a side that's 2 hash marks, 1 hash mark. We've also got this angle here, which is reflexive to the big triangle. And we notice in the big triangle, this corresponding side has 1 hash mark, 1 hash mark, 2 hash marks, 2 hash marks. And if you remember from our unit on dilations, we can say that these two triangles are congruent by SAS similarity. I mean, not congruent, they're similar by SAS similarity, right? This big side here is double this side. Big side is double this side. So these sides are in proportion by a scale factor of 2, and this angle is congruent by the reflexive property. So why is that helpful? Well, if these triangles are indeed similar, then I know that their corresponding angles are also similar, are also congruent. So if I've got a right angle here, I know I've got a right angle here as well. In addition to that, if this is a straight line in 180 degrees, I know that if this is 90, this side is also 90. I can also say that BD is equal to DB by the reflexive property. So because of that, I now have that, maybe I'll call this F over here. I can say that triangle ABD is congruent to triangle FBD. Just do that right. And what property would tell me that these two triangles are congruent? Side, angle, side, side, angle, side. By SAS congruency. So how does that help us find the length of AB right here? Well, by CPCTC, PA is going to be congruent to FB. This side right here, these are in correspondence. And I already know that FB is equal to C over 2, so that means AB is equal to C over 2 as well.